Hello everyone, my name is Gary Wang, and I will introduce Prism removes consensus bottleneck for smart contracts. Prism is a recent blockchain consensus protocol that can scale up its performance. Before I start, I would like to introduce my collaborators. They are Shaw, Vivek, Devi, and Pramod. Blockchain consensus protocol, especially the longest chain protocol, has inspired open platforms for decentralized applications, also known as smart contracts. In these platforms, the nodes participate in the protocol and run various types of smart contracts. For example, in Ethereum, the most popular open smart contract platform, we have popular applications such as ERC20 and CryptoKitties. How well is the performance of these smart contract platforms? There are three elements of the performance. They are security, transaction throughput, and confirmation latency. For Ethereum, it is secure against 50% of adversarial hash power, so we can say its security is pretty good. What about throughput and latency? Ethereum's throughput is less than 20 transactions per second, and confirmation latency ranges from minutes to hours, depending on your target confidence. This means that the platform can only process 20 transactions per second, and you have to wait for a long time to confirm your transaction. The throughput and latency is pretty bad in Ethereum, and they can cause severe problems. For example, when CryptoKitties made its debut on Ethereum, a large number of transactions rushed into the system. The pending transactions were getting dropped, and users have to use a high transaction fee to get transactions included. Therefore, we can say it is very important to scale up smart contract platforms' performance. So let us ask this question. What is the bottleneck of this performance? To see the bottleneck, let us first see its general architecture. Smart contract platforms are based on peer-to-peer networks, consist of interconnected machines. Each machine in it runs a consensus protocol and also runs a virtual machine. And let us look into each machine. So there are two modules. The first is the consensus protocol module, and the second is virtual machine module. The consensus protocol module communicates with other peers and confirms a list of transactions. It then pushes this ordered list of transactions to the virtual machine module. The virtual machine executes these transactions in that order and updates the state, which is usually stored on a database. For most smart contract platforms, including Ethereum, the bottleneck is the consensus protocol module. They use Nakamoto's longest chain protocol or its variant. Let us briefly look at how the longest chain protocol works. Miners try to include transactions into a block by solving a proof-of-work hash puzzle. If they succeed, this block is appended to the current longest chain, and these transactions are included in the ledger. However, the longest chain protocol is limited. The block size, that is, how many transactions a block can carry, is limited to around 200 transactions per block. The block mining rate, that is the time it takes to generate a block, is limited to about 15 seconds per block. As a result, the throughput can only achieve around 13 transactions per second. So one may ask, can we increase the mining rate or increase the block size? Sadly, the answer is no. because if we increase the mining rate, then the forking rate of a blockchain will be increased, and the blockchain structure will look like this figure. The longest chain growing rate will not increase as the mining rate increases. As a result, security is compromised. Similar things will happen if we increase block size. So what can we do for this problem? And natural thinking is we found a better consensus protocol and replace the longest chain protocol. In this work, we removed the bottleneck of consensus protocols for smart contracts. We achieved this by implementing a recent permissionless consensus protocol named Prism, which achieves near optimal performance with zero guarantee. And first, let me briefly introduce how Prism works. Prism deconstructs blockchain by using three types of blocks. They are proposer blocks, voter blocks, and transaction blocks. Proposer blocks forms a proposer blockchain, but it does not use the longest chain protocol. We will see how it works after we introducing voter blocks. Voter blocks forms many parallel voter chains, and the role of voter blocks is to vote for a proposer block. This voting happens for every voter block in every voter blockchain. In each level in the proposer blockchain, the one proposer block that gets the most votes will become the leader proposer block, and those leader proposer blocks forms the ledger. Why do we need so many voter blocks and voter chains? A brief explanation is that with this many voter blockchains, we can confirm leader proposer blocks with a higher confidence and with lower latency. Okay, then let's look at transaction blocks. Transaction blocks are the blocks that actually carries the transactions. And they do not have a chain structure, which means the mining rate of transaction blocks can be very high. Transaction blocks are referred by proposer blocks via a pointer. One proposer block can refer to as many transaction blocks as possible. This just means one proposer block can refer to many transaction blocks, and one transaction block can contain many transactions. As a result, one proposer block can refer to a large number of transactions, and by this way, Prism increased the throughput to a very large number. To conclude, proposer blocks and voter blocks ensures fast confirmation, and proposer blocks and transaction blocks provide high throughput. So now, we have a very promising consensus protocol, and in this work, we implement a full-node smart contract client by adopting Prism as the consensus protocol. We also put two virtual machines on top of Prism. One is Ethereum's EVM, the other is Libra's Move VM. These two projects are open source, so their code is accessible publicly. From here, I will refer to the implementation with EVM as EVM Prism, and implementation with Libra's Move VM as Move VM Prism. I would like to notice that not every consensus protocol can integrate with another smart contract virtual machine. So here, let me introduce several key design and implementation highlights that make Prism consensus protocol suitable for both of these two VMs and distinguish Prism from traditional consensus protocols. The first highlight is that Prism can provide high confidence confirmation. Let's first look at traditional consensus protocols, such as the longest chain. In the longest chain, we have to wait for one block to be several blocks deep in the longest chain, for example, 6 block deep. But these depths can only achieve a very low confirmation confidence. For example, if we wait for a block to be 6 deep, then the confirmation confidence is less than 0.99. A very easy way to increase this confidence is just to wait for more depths. The problem is that the depth is also related with your confirmation latency. If you want to achieve a high confidence, you have to wait for hundreds or even thousands deep. This will increase several orders of magnitude of your confirmation latency, and is unacceptable for the users. Hence, there's not much we can do for longest chain protocol. We have to live with this low confidence. As a result, the VM has to handle many states of many blocks at the same time, which adds complexity to the implementation. Luckily, recall that one advantage of Prism is that it provides a very high confirmation confidence with a relatively low confirmation latency. In our experiment, it can achieve a high confirmation confidence that is greater than 1 minus 10 to the minus 9 power. With this high confidence, it is very unlikely that any transaction is reversed. This means that the implementation of the virtual machine only needs to maintain the latest confirmed state. Only under very rare cases, the virtual machine needs to handle state switch or state reverse, and these rare cases usually will not happen. In addition, this confirmation advantage also makes the Prism consensus protocol to be suitable for those BFT-style virtual machines, such as MoveVM, because in the BFT consensus protocols, there is no such thing as reverse. So virtual machines, such as MoveVM, also only maintains the latest confirmed state. This is the reason why Prism is suitable for MoveVM, but the traditional longest chain protocol is not. The second highlight is Prism decouples transaction validation and state update from consensus. By design, Prism does not validate transactions when it mines blocks. As a result, when the Prism consensus protocol pushes the ordered list of transactions to the virtual machine, this list could contain invalid transactions. This deviates from traditional blockchains such as Bitcoin or Ethereum, which has to make sure that every transaction in the blockchain is valid. But does this cause any problem for Prism? The answer is no, because the virtual machine is smart. It runs smart contract. So the virtual machine itself can decide whether the transactions are valid or not. Let's look at this very simple example. Say there are 6 transactions, and the first is valid, the second is not valid because there's not enough gas, the third is valid again, and the fourth is invalid because not enough balance, the fifth is invalid because the wrong nonce, and the sixth is valid. The virtual machine runs the transactions one by one, and whenever it encounters an invalid transaction, it just skips this invalid transaction and continues to the next transaction. In this way, invalid transactions are removed from the ledger and keeps the ledger valid and also keeps the state in the database consistent. As you can see, the second, fourth, and fifth transaction in this list are just skipped and removed from the ledger. The third highlight is that there is no pending transaction exchange in Prism. In traditional protocol, a transaction is broadcast from one machine throughout the network. At the meantime, all the machines are mining, trying to include this transaction into the next block. Once one machine succeeds in mining, it produces this block, and it will broadcast this block throughout the network. As a result, actually every single transaction is broadcast twice throughout the network. The first time is as a single transaction. The second time is included in a block. Okay, let's look at what happens in Prism. In Prism, because the mining rate of a transaction block is so fast, you can easily produce hundreds of transaction blocks in 1 second. So, when you have a transaction, you only need to wait for less than 1 second to get this transaction included in one transaction block, as shown in this figure. And this transaction block is then broadcast throughout the network. The result is that every transaction is only broadcast once. Compare Prism with traditional consensus protocol, we can see that Prism saves half the bandwidth for broadcasting transactions. Okay, these are the 3 highlights that distinguish Prism from traditional consensus protocols. Now let us look at the evaluation of its performance. We have the full node client of EVM and MoveVM with Prism. Also, we have implemented 2 baselines that are EVM and MoveVM executor only. These baselines are programs that feed transactions to the virtual machine running on a single node, and they demonstrate the optimal throughput of the virtual machine. This also means that these baselines are not related with consensus protocol. To run the experiments, we chose 6 applications on the virtual machines. The first is native payment, that is payment of Ether in EVM and payment of the Libra coin in MoveVM. The second is do nothing. It literally does nothing. The third is ERC20 token. It is a token standard that everyone can create, and the tokens can be transferred. The fourth is CryptoKitties. It is a very popular contract on Ethereum, so it is not applicable on MoveVM. Fifth is CPU heavy, which does a lot of computation inside the contract. The sixth is IO heavy, which does a bunch of reads and writes on the database. We also found that the size of the state, that is the number of accounts in the state, also influence the performance. So we use 10,000 accounts in the state. The accounts are created at the beginning of the experiment, and every account is offered with enough tokens. So let's look at the throughput of EVM Prism. This is the results. We can see that for the 6 different applications, the throughput is quite different. This is because we wrote these smart contracts differently, and these smart contracts have different complexity. What is important is that for every application, we compare the throughput of EVM Prism with EVM executor only, which is the optimal throughput or the upper bound. We can see that for every application, EVM Prism is very close to the EVM executor only. Actually, EVM Prism can achieve more than 85% of EVM executor only throughput. This indicates that Prism consensus is not the bottleneck anymore. The virtual machine itself is the bottleneck. Compared to the throughput of Ethereum, which is around 20 transactions per second, it is clear that Prism EVM has throughput of a few orders of magnitude higher than Ethereum. Because Prism changes the consensus protocol but not the virtual machine, we can say that, again, Prism removes the consensus bottleneck. As for confirmation latency, in our EVM Prism experiment, confirmation latency is around 2 minutes with confidence around 1 - 10 to the -9 power, when adversary hash power is 40%. This confidence is pretty high. If we use the traditional longest chain protocol to achieve this high confidence with the same hash power, we have to wait for hundreds of blocks, and it translates to thousands of seconds in terms of confirmation latency. This figure shows the instant throughput of our client. We can see that around the first few seconds, there is no throughput because there is not enough blocks to extend the ledger. But soon after the first few seconds, the throughput starts to grow and become stable around 30,000. This shows that our Prism client will become stable very soon. For MoveVM, the result is similar. The MoveVM Prism throughput can reach about 80% of MoveVM executor-only throughput. This means that MoveVM Prism can remove the consensus bottleneck because of the Prism consensus. We did not compare this throughput to the Libra's throughput because Libra is a permission consensus protocol, whereas Prism and most traditional blockchain protocols are permissionless. The above experiments are running on 100 EC2 nodes. We also did a scalability experiment that runs the experiment on 300 EC2 nodes, and the performance stays at the same level as the number of participants increase. So Prism consensus and also our implementation of the client can scale with more number of nodes. To conclude, we have shown that Prism fits with two smart contract virtual machines, EVM and MoveVM. In the evaluation, we show that Prism removes consensus bottleneck for Ethereum, EVM, and similar results also show in MoveVM. Now that Prism removes the consensus bottleneck, the bottleneck now is the virtual machine itself. Hence, future improvement on the virtual machine would be beneficial to the performance. Thank you all for listening.